All right, welcome everyone. Let's get started. So today we're going to continue on with learning outcomes O1 and we'll start O2. So we're going to keep talking about graphs of functions and how it relates to f prime and f double prime. And then we'll look at our first optimization technique in learning outcome O2. But before we do that, I just want to remind everyone, this week is recitation exam 4 during your scheduled recitation time. So for the new material, the test questions on the new material, there's going to be 5 questions. They're going to be testing learning outcomes D5. So being able to prove some of our basic derivative rules. So derivative of our other trig functions like tan, secant, cosecant, cotangent. Being able to prove our derivative rules for inverse trig functions using implicit differentiation, and being able to prove our derivative rule for our log functions, also using implicit differentiation. So, that's D5. Being able to prove some of our basic derivative rules, either using product rule, quotient rule, or chain rule, or for the inverse functions using implicit differentiation. And then in D6, that was just derivatives of more complicated functions. So functions where you might need to use product rule, quotient rule, chain rule, some combination thereof. So you might have to use more than one rule in your work, or you might have to use logarithmic differentiation. So D6 was just more complicated differentiation. And then there will be a test question on section DA1, so exponential growth decay. A test question on learning outcome DA2, linearization, so basically tangent lines, something we've talked about quite a bit. And then learning outcome DA3, so L'Hopital's rule. And then there's the follow-up questions from the last exam. So when you're kind of setting down to study, make sure you know which questions from exam 3 you need to redo on this follow-up exam for this week. All right, so let's keep going with our new material. And so in learning outcome O1, we're looking at kind of a lot of the definitions and terminology, and a lot of the kind of the building blocks for what we're going to do in the rest of this unit. And it all has to do with ultimately optimization techniques and being able to describe the graph of a function. And that's what we're going to do in this example. We're given a few properties of some function f, and we're going to sketch what function f might look like. All right, so let's start with the first property there. It says f of 3 is equal to 4. Now, this information tells us that we have a specific point on the graph of our function, and it tells us the point 3, 4 is on the graph. And why 3, 4? Well, the number inside our parentheses here, that's the x coordinate. And the y value is just the value of our function. So at x equals 3, the function value is equal to 4. X is equal to 3, y is equal to 4. So that point must be on our graph. So let's plot that point. So we find 3, 4, and we're going to plot a point there. All right. Now let's look at the next piece of information. It says f prime of 3 is equal to 0. And what this tells us is that we have a horizontal tangent line at x equals 3. So when our derivative is 0, it means the slope of the tangent line is flat. So just to remind us of this, let's graph in a little piece of the tangent line, and it's going to be flat. It's going to be horizontal. So we'll just kind of make it a flat horizontal line there, right through our point at x equals 3. And that tells us our graph needs to be flat there. All right, what else? Well, we're told that f prime is greater than 0. So f prime is positive when x is less than 3. And this is where we left off last week. When our first derivative is positive, our function is increasing. And when our first derivative is negative, the function is decreasing. So that's what we have here. F prime is positive when x is less than 3. So what that means is f of x is increasing for x less than 3. And then we see f prime is negative when x is greater than 3. So that means if f prime is negative, that means our original function f must be decreasing when x is greater than 3. So we see there's a lot of x equals 3 is really, there's a lot happening there. So let's kind of we'll draw this out. So at x equals 3, our derivative is 0. So our graph flattens out. If x is greater than 3, so that means we're on this side. What's happening if x is greater than 3? Well, we said that our function was decreasing. So on this side, our function, when we draw it in, needs to be decreasing. And when x is less than 3, that means we're on this side of the x, of this side on the x-axis, then it means our function is increasing there. And that's what we saw with the property that f prime was positive when x was less than 3. So on the left side there, our function is increasing, and on the right side, our function is decreasing. So let's sketch in what a potential graph might look like that is increasing on the left side and then switches to decreasing on the right. And when we draw this in, it needs to flatten out right at x equals 3. So it needs to flatten out there. And so that's just one potential example. It's increasing on the left, it flattens out right at x equals 3, and then it switches to decreasing on the right. So that's just one potential example of what this function might look like based on those properties. You might draw something a little bit different. But based on those properties, this fits all 4 of those properties. All right, let's now talk about the second derivative. And that's what we're going to look at here. And we have this second derivative rule. And the second derivative rule is related to the shape of our function. It's related to concavity. So first derivative tells us increasing, decreasing. The second derivative tells us concave up, concave down. So if f double prime is positive, then that means our function is concave up. And if f double prime is negative, then that means our function is concave down there. So let's just kind of talk about this a little bit more. So if f double prime is positive, it's greater than 0, that means f prime, if the second derivative is positive, then that means f prime is increasing. And if f prime is increasing, that means the slope of our graph is increasing, which is one of our definitions for concave up. So if the slopes of f are increasing, and I probably should put slopes there, if the slopes of our function are increasing, well, that's one way to define concave up. So let's look at what, potential examples for an increasing function are. So if f is increasing, that just tells us the general trend. So it means it's going up like this. And so if our function is concave up, what our concave up function is doing is it has an upward bend to it. So this is what an increasing function that's concave up might look like. So it has our tangent line, which is increasing, and then it has an upward bend to it. If f is concave down, what does concave down look like? So if f double prime is negative, that means f prime is decreasing. And if f prime is decreasing, that means the slopes of f are decreasing. And that's just one way to define concave down. So if f double prime is negative, well, then our graph could still be increasing, but it has a downward bend to it. So it's bending downward. So concave up sits above the tangent line, concave down sits below the tangent line. So those are just two examples for an increasing function. If f is increasing and it's concave up, it would look something like that. And if f is increasing but concave down, then it would look like the curve that's bending downward below the tangent line. Similar idea for decreasing. So if f is decreasing, what would the graphs look like there? Well, decreasing describes just the general trend of our function. So it's a downward trend here. So it looks something like that. And if f is concave up, it's going to bend above the tangent line. And if it's concave down, then it's going to bend below the tangent line. So the graphs would look something like this. Concave down bends below, concave up bends above. And that really reflects the shape of our graph. So increasing, decreasing just kind of gives us the general trend if our function's going up, going down. But concave up and concave down really describe the shape of how our graph kind of curves and bends and all of that. All right, so let's see an example where we have to sketch the curve. So let's look at this where we're given a few different properties, kind of unravel what each of these mean, and kind of sketch an example of what this function might look like. So let's start with the first property. It says f of 1 is equal to 2, f of 2 is equal to 3, and f of 3 is equal to 4. And those are just telling us various points on this curve. So the first one there tells us 1, 2 is on our graph. The second one here tells us 2, 3 is on our graph. And the third point, or the third value there, gives us a third point, 3, 4 is on our graph. So all of these are on the graph. And again, the value inside the parentheses there is our x value, and then our actual value of our function is the y value. So let's plot all of those points. We have 1, 2, we have 2, 3, and then we have 3, 4. So we have those 3 points on our graph. Now, what other information do we have? Well, it says f prime of 1 is equal to 0 and f prime of 3 is equal to 0. So when our derivative is equal to 0, that means we have a horizontal tangent line. So we're going to have a horizontal tangent line. The graph flattens out at x equals 1 and x equals 3. So let's draw in horizontal tangent lines at those two x values, at those 2 points. So our graph is going to flatten out at x equals 1. Do a little better than that. Yeesh. One more time. Good enough. At x equals 1, flattens out. Let's draw a little bit of a tangent line there just to remind ourselves that when we sketch in the result, it needs to flatten out there. And then it also flattens out at x equals 3. So we'll draw in a little tangent line there just to remind ourselves that the graph is going to flatten out at x equals 3. All right. So far we have a little bit of information at what's happening at those particular points. Now let's look and see what other information we have. And what we have is based on our second derivative. So let's go down to our property, our fourth property there. It says the second derivative is greater than 0 for x less than 2. So if f double prime is greater than 0, that's telling us f double prime is positive. So when f double prime is positive, that means f of x, the original function, is concave up. So for x less than 2, our graph is going to be concave up. It's going to have a concave up shape. Now what about that last property? It says the second derivative is less than 0, so the second derivative is negative. And when f double prime is negative, that means our function is concave down. So it's concave down, and we're given the interval for x greater than 2. So something's happening there at x equals 2. So let's kind of plot this all along the x-axis here. At x equals 2, what's happening? So on the right side, we have what's happening directly at x equals 2, and then x greater than 2, and then x less than 2. And what we've just seen is that when x is less than 2, we're on the left side there, our graph is going to be concave up. And when x is greater than 2, we saw that our graph is going to be concave down. So let's draw in what happens when we have a concave up shape on the left. And concave up means it looks something like this, and concave down means it's going to look something like this, or pieces of those U and upside down U shapes. But we see that we need to have a horizontal tangent line at x equals 1, so concave up means it has to kind of hit a low point at x equals 2, and then keeps going like that. And then at x equals 3, we also have a horizontal tangent line, and it needs to be concave down. So it needs to have this sort of look to it. And so this is just one example of what this graph might look like. And what we're seeing there is that to the left of x equals 2, our graph is concave up. To the right, it's concave down. And so the third property here that we haven't talked about really is we're seeing a switch in concavity at x equals 2. So if f double prime of 2 is equal to 0, and we see we have a switch in concavity there, this means we have an inflection point. At x equals 2. So this point here is an inflection point on our graph. So we have a change in concavity at that point. Goes from concave up on the left to concave down on the right. Now there's a few other things we might notice here. When we sketch this in, we drew a local minimum at x equals 1. And that's the only way to correctly draw this graph based on these properties. So we have a local min at x equals 1. It's a local minimum. It's a low point on our graph. And that's the only possible way where we could have a horizontal tangent and have that concave up shape. And then same thing at x equals 3, we see that we have a local max. And that's the only way we could have drawn this correctly, where we know we have a horizontal tangent and a concave down shape. That's the only possible way we could have drawn it. And we'll see why in a few sections, but for right now, we're just kind of trying to develop just an intuition about what these different definitions and gadgets, how they reflect in the graph of a function. All right, so let's try another example. So let's say we have the graph of our function f, and we want to sketch the graph of its derivative. There's a few ways to do this, and one way is to pick a few different points along the curve, as we see here. So we have a few different points along the curve there, and then draw in the tangent line at each of those points, and then estimate what the slope of the tangent line is for each of the ones you've drawn. So we're not going to show that step. That's something we did a while ago. But right here at x equals 2, we see that we've drawn in a little example of what the tangent line might look like. And if we were doing this by hand, we would kind of just estimate what the slope of that line is. And here it's actually stated for us. The slope of that tangent is equal to 4. And it's repeated along all those points along the curve. So at x equals 1, we drew in our tangent line, estimated what the slope of that line was, and found it was 6. Same thing at x equals 4. We drew in what our tangent line is, and and this one's not too bad. It looks like our graph flattens out there at the top. So whenever we have a flat tangent line, that's where our slope is 0. And then same thing at x equals 6. We drew in a tangent line, estimated the slope of that line, saw it was -4. So that's the general procedure for how to estimate one way to graphically estimate the slope of the tangent line is to draw it in and then just estimate the slope. It's just change in y over change in x. So assuming we've done that for all these different points, let's use those results then to graph f prime. So that's what we're going to do. We're going to use those different values to graph f prime. All right, so let's start with x equals 1. Let's start with x equals 1. And we see that the slope of our original function f of x is equal to 6 there. So that tells us at x equals 1, the point 1, 6 is going to be on the graph of f prime. What about at x equals 2? Well, at x equals 2, we estimated that the slope of our curve is 4 there. So that tells us the point 2, 4 is on the graph of f prime. Then at x equals 4, we estimated looked like a horizontal tangent line, so the slope we estimated was 0 there. So that would tell us then that the point 4, 0 is on the graph of f prime, graph of the derivative. And we keep doing this. So at x equals 6, we estimated the slope of the tangent line to be -4. So that means the point 6, -4 is on the graph of f prime. And finally at x equals 7, we estimated the slope of our curve was -6. So that means the point 7, -6 is on the graph of f prime. And so the values of the y values there are just the slopes of our original function f. So the y value for f prime is just the slope of our function at that x value. Now, for this function, the graph of f prime is going to be a line, so we can just connect the dots. Oop. And hopefully with a line. Let's see how this looks. Not too bad. This is something with a line. This is just a sketch, so we just want to capture the general behavior of f prime here. And really the general behavior is really, we can see there's interesting behavior happening at x equals 4. The graph has a local maximum there. And then we also see that f prime kind of crosses the x-axis at x equals 4. So x equals 4 is really kind of splitting up. There's different behavior on each side of this x value. And let's kind of draw a chart, kind of summarizing what we see. So x equals 4 really splits up the x-axis here in terms of the behavior on each side. So the interval to the left, minus infinity to 4, and then the interval to the right, 4 to infinity. So let's look at the left side there, from minus infinity to 4. Let's see what we notice about f prime and what we notice about f. So on the left side there, we see that all of the slope values were positive. And if we look at the graph of f, we also see that it's increasing. So that just confirms, what we know about the relationship between f prime and f. F prime is positive, then our function's increasing. If our function's increasing, then f prime is positive. On the right side, so when x is greater than 4, or we're in the interval from 4 to infinity, there we saw f prime was decreasing. So the graph was moving down. And we looked at our slope values and saw the slope values were negative. So the derivative values were negative on that side. And that's precisely what we're seeing here. So this sort of sign chart analysis is something we're going to be doing quite a bit in the upcoming sections. But let's just kind of point out that at x equals 4, we have a relative maximum. We have a local maximum at x equals 4. And so what's happening at x equals 4 is the derivative is switching from positive to negative at x equals 4. And that gives us a maximum. For a minimum, it would be if we saw a switch from minus to plus. So if our derivative went from negative on the left to positive on the right, we'd have a minimum. So just some interesting behavior to kind of keep in mind there. All right, let's try another one of these. So here we're given the graph of some function f, and we want to sketch the derivative and just kind of talk about the behavior that we notice in regard to f prime, and possibly f double prime. So we've gone through and picked a few points along the curve and just estimated what the slope is of our curve along those points. So let's go through and plot them again, just like we did in the last example. So at x equals 1, we estimate that our slope is equal to 11. So this is going to be our graph of f prime here. So that means 1, 11 must be on the graph of f prime. If we go to x equals 2, go to x equals 2, we estimate that our slope is equal to 6 there. So let's plot 2, 6 on our graph. And then at x equals 4, our slope we estimate is 2. So let's plot 4, 2. And then at x equals 6, we estimate that our slope is 6. So that means the point 6, 6 is on our graph. So we plot that one. And then finally, if at x equals 7, we see that we estimate that the slope is 11 there. So let's plot 7, 11. And we're just going to then kind of connect the dots. And it looks like we're getting a parabola shape. So maybe something like this. So we're just sketching the graph of f prime, just trying to capture the overall behavior of what f prime might look like. But let's kind of talk about what another way to think of this in terms of f double prime, in terms of the shape of our function f. So what do we notice if we look at function f? In this section here, the graph looks to be concave down. It has that sort of downward bend to it. And then on this section over here, it looks to be concave up. So it has part of that U shape, that concave up U shape. So on the left portion of our graph, it looks concave down. On the right portion, it looks concave up. And then possibly right there at x equals 4, it looks like that's where the transition might happen. It goes from concave down to concave up. And so x equals 4 is really splitting up the kind of the behavior of our function. So let's do another sign chart. Plot x equals 4. And then we have the interval on the left, and then the interval on the right, 4 to infinity. And what do we notice about f on each of those intervals? Well, on the left interval, we notice that it was concave down. And on the right interval, we notice that it's concave up. And so what that means for f double prime, if f is concave down, that means f double prime is positive. Or negative, and if f is concave up, then that means f double prime is positive. So f double prime must be positive on the right side here. And if f double prime is negative, what does that tell us about f prime? So if f double prime is negative, that means f prime must be decreasing. And if f double prime is positive, that must mean f prime must be increasing. And that's precisely what we see on our sketch. Is on the left side, it's a decreasing, our sketch of f prime is decreasing, and then on the right side, it's increasing. So just by identifying the shape of our function, that also tells us information about f prime, if f prime is decreasing or increasing. And we just point out here that our graph, original graph of f of x, has an inflection point at x equals 4. So there's an inflection point at this x value. And that's because it looks like our graph goes from concave down to concave up. It switches concavity there. And it's just an interesting observation that when our graph has an inflection point, the derivative, f prime, has a local max or a local min. So just a little observation there. When our graph has an inflection point, then f prime has a local min or local max. And if f prime had a local min or a local max, then that would actually tell us f has an inflection point. All right, let's try looking at the graph of f prime and trying to recover information about the original function f. So here we're given the graph of f prime, and we're going to try to figure out what properties does function f have based on this graph. So in the last examples, we were given graphs of f and tried to sketch what f prime might look like. Here we're given f prime, and we want to try to figure out what f might look like. So first part there, what is the slope of the graph of f when x is equal to 1? So really, just to emphasize this, the curve that we're seeing here it's f prime, it's the derivative. We want to find out information about f. And so the way we read this graph, we want to answer the question, what is the slope of f when x is equal to 1? Well, the slope of f of x at x equals 1 is equal to, that's exactly what the derivative tells us. If we were to evaluate the derivative at x equals 1, that would give us the slope of f of x at x equals 1. So let's go through, find x equals 1 on the graph, figure out what the point is there. So the point is 1, 2, and that value 2, that's the value of our derivative at x equals 1. So that tells us the slope of f at x equals 1 must be equal to 2. All right, second part there. For what values of x does the graph of f have a horizontal tangent line? So we know this happens, we have a horizontal tangent line whenever f prime of x is equal to 0. So if we're given the graph of f prime, what we want to look for in this case are the x-intercepts. Where does f prime cross the x-axis? So we look along our x-axis there. We see where the graph touches the x-axis, and we see a point right there, looks to be at x equals 3. So that's an x-intercept, where it crosses or touches the x-axis there. And so what that tells us about our function f is that we have a horizontal tangent line at x equals 3. The graph flattens out. All right. All right, so we figured out the slope at x equals 1. We figured out where the graph has a horizontal tangent line. Now let's figure out the intervals where f prime is positive and negative. So if we look, f prime is positive when it's above the x-axis. So that's what we're seeing here. On this section of the graph, f prime is above the x-axis. And then f prime is negative when the graph goes below the x-axis. That's what we're seeing over here. The graph goes below the x-axis. So to summarize, f prime is positive on the interval from -infinity to 3. And we just assume here, we're just kind of reading this graph based on what's presented. So we just assume that the graph just kind of keeps on going like this all the way to the left. Same thing down here. we just kind of read this as it just continues on this way for forever, all the way to the right. So what we're seeing there is that to the left of x equals 3, our f prime is above. That makes it positive. And then on the other side, f prime goes below the x-axis. So on the interval from 3 to infinity, f prime must be negative. Now, if f prime is positive on the interval from minus infinity to 3, that means f must be increasing on that interval. And if f prime is negative on the right interval, 3 to infinity, that means f must be decreasing on that interval 3 to infinity. And so what we've seen is that our graph of f must be increasing on the left, decreasing on the right. So if we kind of sketch in what f prime, and we also notice that f prime before, f prime is equal to 0 directly at x equals 3. And so what we're seeing is that f prime, or f, is switching from increasing to decreasing. So if f is increasing on the left, the general trend is up. And then, and let me draw it over here. So at x equals 3, on the left of x equals 3, our function must be going up. And then to the right of x equals 3, our function must be going down. Just general trend. And we can see if we draw a really rough sketch there of what f might look like. This is just a really rough sketch. We haven't looked at any of the shape of our actual function, just looking at kind of the general behavior. It's going up, it's going down. If we just sketch in what f might look like, if it's increasing on the left, decreasing on the right, we have to have a local max there in the middle. So that's just kind of the general behavior of function f. We've identified where it's increasing, where it's decreasing. Now let's think about the shape of our function. So let's see if we can determine where f might be concave up, concave down. So if we look at the graph of f prime here, let's figure out where f prime is increasing and where it's decreasing. And again, we're just kind of assuming that all the way to the left it just keeps going like this, all the way to the right it just keeps going down like that. So this is the graph of f prime, and what we see is f prime is decreasing that whole interval. So f prime it's never increasing. There's no interval, there's no place where f prime here is increasing. As we read this from left to right, f prime is always moving downwards, so it's always decreasing. So it's decreasing on the interval from minus infinity to infinity. So if f prime is increasing, that must mean f double prime is positive. But if f prime is never increasing, that means f double prime is never positive. So there's no interval where f double prime is positive. And if f prime is decreasing, that must mean f double prime is negative there. So f double prime is negative on the interval from minus infinity to positive infinity. Now, why is that the case? Why is this? So let's suppose we had f was increasing. If we know f is increasing, then we know f prime is positive. That's how the function and its derivative are related. Now, if we were to apply the derivative to all of that, the relationship still holds. So if we apply the derivative to the top part there, it tells us f prime would be increasing. And if we apply the derivative to the second part of that statement, that would tell us f double prime is positive. So we're just applying the derivative to this top part and this bottom part here. So if f is increasing, if we apply the derivatives to that, we get f prime is increasing. And so the relationship holds. If f is increasing, f prime must be positive. If f prime is increasing, f double prime must be positive. Same thing goes for negative and decreasing. So that's how we can get this relationship. If we know f prime is decreasing, then that means f double prime must be negative. And if f double prime is negative, that means f is concave down. And we see that since f double prime is never positive, that means f itself must never be concave up. There's no interval where the graph of f must be concave up. So just given this graph of f prime, we're able to figure out the shape of f. So we are able to figure out where the original function f is concave up, concave down. We're able to figure out where the original function f is increasing, where it's decreasing. We're able to figure out where it has a local maximum. And then we're also able to figure out where it has horizontal tangent lines and just what the slope of our function could be at any particular x value. So the graph of f prime, even though it's the derivative of f, still tells us quite a lot of information about what the function f must be doing. So it gives us quite a bit of information. And that's what we're going to see in the next, kind of the next section here, is we're going to use derivatives to kind of introduce our first optimization technique. And so we're going to look at kind of one of the major results, the extreme value theorem, and we're going to see how we can use this to find the absolute maximum and the absolute minimum values of a function where we have a continuous function on a closed interval. So we're going to start by just kind of reading through the extreme value theorem. If f is a continuous function on a closed interval, then that function is guaranteed to have an absolute maximum and an absolute minimum value somewhere on that interval. So it's guaranteed to have a high point and it's guaranteed to have a low point. Now the issue is this doesn't tell us where it happens. So it could happen anywhere inside that interval, but it tells us somewhere in that interval we're guaranteed to have a max, an absolute max, and an absolute min. So let's look at the graph on the left there. This function, this curve that's sketched is continuous. There's no jumps or holes or breaks. So it's continuous on the closed interval from 1 to 8. So we notice that this function is continuous. We're talking about a closed interval from 1 to 8. And so just those two conditions, f is continuous and we're talking about a closed interval, that's enough to guarantee that this function has to have an absolute max and an absolute min. And we can see that. So if we look on the graph there, the highest point we ever get happens at x equals 8, and the value is equal to 6. So that's the highest point on our graph there at x equals 8. The lowest point, that's our absolute min, this happens at x equals 6, and the value there, the absolute minimum value, is 1. So that first graph is an example of a function that satisfies the necessary conditions for the extreme value theorem. It has to be continuous on a closed interval. If we go to the middle graph, let's see what happens if we get rid of the closed interval part. So if f is continuous, f is still continuous here. There's no jumps or breaks or anything like that in the middle. We've just excluded one of the endpoints now. So it's continuous on the interval from 1 to 8, where we include the endpoint 1, but we're excluding the endpoint at x equals 8. So this is not a closed interval. So that interval is not closed. It doesn't contain its endpoints. So, the function's still continuous. It's just not a closed interval. And unfortunately, the extreme value theorem needs both of those in order to guarantee our function has an absolute max and an absolute min. So that's what we're seeing in this case here. If we were to look for an absolute max value, it just doesn't exist. There is no absolute max value of this function. And the reason is because the only potential candidate is that one at 0.86, but that's not included on our graph. So if I were to pick any point, maybe something just below it, if I were to pick any point there, I could zoom in and I would see still a little gap there where I could potentially pick a point slightly higher. And if I pick that slightly higher point, I could zoom in further and find a little section of curve where I could go a little bit higher. And so I could keep playing that game. I could keep going closer and closer to that open dot without ever reaching it. And so that graph does not have an absolute max. There's no one high point, absolute high point of that curve. There is this local max that we're seeing here, but that's not the absolute max because there are other points along the curve that are higher than that point. So any of these points in this little section here are higher than that local max. So that local max would not be an absolute maximum because I can find other points on the curve that are higher. But if I pick any of those other points, I can kind of keep working my way up. I can find another point that's slightly higher. Then I can find another point that's slightly higher. And I can keep going by picking points slightly higher. So there is no absolute max. But there is still an absolute min. So, we might still have something. We're just not guaranteed to have it. So this is an example where it's a continuous function, just not on a closed interval. So we don't have an absolute max, but we do have an absolute min. On the next graph, let's see what might happen here. So here, f is not continuous. So we're still talking about the closed interval from 1 to 8, but now we see a break in our graph at x equals 6. So the function is not continuous on that closed interval. We're still talking about a closed interval. And does our function have an absolute max? Does our function have an absolute min? And that's what we want to find out. Now in this case, it does have an absolute max. So the 0.86 is the highest point on our graph here. So we have a absolute max at x equals 8. But there's no absolute minimum. So kind of the potential place for an absolute minimum would be right in here. But if I pick any point there that I'm going to say is my absolute minimum, say I pick this point here, that's my absolute minimum. Well, I can find a little section of curve just below it where I could go a little bit further. I can go down a little bit further. But that point's not the absolute minimum because there's still a tiny little section of curve there where I could pick another point. And then that other point is still not the absolute min because I could go a little bit further. And I could keep playing that game. I could, if I pick a point, there's still going to be a little section of curve further down where I could pick another point. And so I could keep doing that over and over. And the fact that we never actually reach this point here means I could keep playing that game for as long as I need to. And so there's no absolute minimum on this interval. All right, so that's the extreme value theorem. If our function's continuous on a closed interval, we're guaranteed to have an absolute max, absolute min. The issue here is it doesn't tell us how we actually find where the absolute max and min occur. So for that, we need something else. We need a theorem, courtesy of Fermat, and it says if f has a local maximum or minimum at x equals c, then either f prime is equal to 0 at x equals c, or f prime does not exist at x equals c. So let's see what just some examples of what might happen. And in the first graph here, we have a local min. So Fermat's theorem says if we have a local minimum, then the derivative is equal to 0 or the derivative is undefined. And what we're seeing in this case is our derivative is equal to 0. We're seeing a graph where the graph flattens out nice and kind of gradually there. We have a horizontal tangent line. Now in the middle graph, this also is a local minimum. Fermat's theorem also works for local maximums too, but just to give some examples here. In this middle graph, we have a local minimum. And in this case, we see that we have a cusp. So we talked about this when we first introduced the idea of differentiability. When we have a cusp at an x value, that means the derivative is undefined, does not exist. So that's another possibility with Fermat's theorem. If we have a local minimum or maximum, the derivative might not exist there. And that's what we're seeing here. And so those places where the derivative is equal to 0 and the derivative is undefined, those are important. These are going to be the potential locations for where we might have a max or a min, and we call those the critical numbers. So the number x equals c is a critical number of f, provided either f prime of c is equal to 0 or f prime of c does not exist. So knowing where the derivative is equal to 0, knowing where it's undefined, those are important. They really give us a lot of information about the behavior of f. So we call those the critical numbers. And then one other requirement for the critical numbers is the value x, the x value there, needs to be in the domain of function f. So our function does have to be defined there for it to be a critical number. Now, unfortunately, knowing that f prime is equal to 0 or f prime does not exist is not enough to guarantee a max or a min. And that's what we're seeing in this third case here. This is an example where the graph does flatten out, so the derivative is equal to 0, but it's neither a max or a min. So just knowing that we have a critical number is not enough information to tell us we have a max or a min. We might have a case like this third graph where the graph flattens out, but it just doesn't have that max or min behavior. So what Fermat's theorem really does is it gives us a place to start looking for maxes and mins. But as that last graph shows, not every critical number of f gives us a local max or min. So it gives us a place to start looking, but we're going to have to do more work to figure out, is it a max or is it a min? All right. So in the context of a function defined on a closed interval, the way we identify if we have a max or a min and a critical number, well, we have this little technique. If we put all the pieces together, we have this closed interval method, which allows us to locate where we have an absolute max or an absolute min. And it turns out that if we do have an absolute max or an absolute min, and we're guaranteed to have them on a closed interval, then they have to occur at either a critical number or an endpoint. So this really tells us if we want to figure out where our function has an absolute max or an absolute min, and we're looking on a closed interval, we want to look at the critical numbers. So where does f prime equal 0? Where does f prime not exist? And we want to look at the endpoints. Those are the only places where we might have an absolute max or an absolute min. Again, just the absolute max is the highest point on it's the largest value of our function. And the absolute min is the smallest value. And so if we're talking about a closed interval, if our function is defined on a closed interval, for the closed interval method, we first just want to verify that our function f is continuous on that closed interval. Then we want to find the critical numbers, and we want to evaluate the function at the endpoints and the critical numbers, and just see which value is the largest and which one is the smallest. So that's what we do. We go through those steps. Once we have the critical numbers, we take the critical numbers, plug them into the original function f, take the endpoints, plug those into the original function f, and we just compare the results. The largest value is the absolute max. The smallest value is the absolute min. So let's see an example. Let's find the absolute max and the absolute min value of the function x cubed plus 3x squared minus 9x minus 7 on the closed interval from -6 to 4. First thing, we just want to verify that f is continuous. And it's a polynomial. So polynomials are always continuous. And we're talking about a closed interval here, closed interval from -6 to 4. So the extreme value theorem says this is a continuous function on a closed interval. We're guaranteed to have an absolute max and absolute min. Now let's see how we're going to find them. So at step 2, we want to do the critical numbers. So to do that, we need to figure out the derivative, and then we're going to set the derivative equal to 0. And we'll see if our derivative is undefined. So those are the two kind of possibilities for a critical number. Either the derivative is equal to 0 or the derivative is undefined. So to do that, we need our derivative. So let's actually calculate the derivative. So if we differentiate this polynomial, it's 3x squared plus 6x minus 9. And we're going to set this equal to 0 and solve for x. So to help us do that, let's factor this. So I can factor out a 3. That gives me x squared plus 2x minus 3. And then I can keep factoring. And so x squared plus 2x minus 3 factors into x plus 3 times x minus 1. So there's my fully factored derivative. So now I want to figure out where that derivative is equal to 0 and if it's undefined. So first I'm going to set my derivative equal to 0. So I take my factored version, set it equal to 0. And with it factored, each of those factors tells me, gives me a critical number. So the factor x plus 3 there gives me the critical number x equals negative 3. And then the factor x minus 1 gives me the critical number x equals 1. And for the derivative not existing, the only way it would exist is, or not exist, is if we had something like division by 0, maybe a negative under a square root, or if it was like a log function or something like that. We just have a polynomial here, so the derivative always exists. So there's no place where this derivative does not exist. There's no division by 0 or anything like that. So what we're seeing here is we have two values here, two x values, and these are our critical numbers. So we have our critical numbers. In step 3 now, this is where we evaluate. So we're going to take the endpoints of our interval, take the critical numbers that we found, and just plug them into the original function and see which one gives us the largest value and which one gives us the smallest value. That's going to be the absolute max and min. So let's start with the critical numbers. Let's start with we'll plug x equals 1 into our original function. So we're going back to the original function now. So we get 1 cubed plus 3 times 1 squared minus 9 times 1 minus 7. And if we do the arithmetic there, we end up with negative 12. Okay, keep going. So we have negative 3 to plug in. So let's plug negative 3 into our original function. We get negative 3 cubed plus 3 times negative 3 squared minus 9 times negative 3 minus 7. And if we do the arithmetic there, we end up with 20. So when we do this evaluation, we're always going back to that original function, because that's what we're trying to do. We're trying to find the largest value of that function. So that's why we're plugging them into that. We're trying to find the largest and the smallest value of that function. All right, so we've done the critical numbers. Now we want to do the endpoints. So there's two endpoints to check. We'll plug 4 in, and I won't write this out, but if we plug x equals 4 in, you do the arithmetic, you should end up with 69. And when we plug in negative 6, you should end up with negative 61. And so the very last step then, once we've found the critical numbers, we've evaluated the function at the critical numbers and the endpoints, the very last step then is just to compare the results. So if we look, the largest value, if we see we have 4 values here to compare. Negative 12, 20, 69, and negative 61. The largest of those values is right there at x equals 4. And so what we see is that we have an absolute max. It's equal to 69, and it occurs at x equals 4. We want to find the absolute min. So this is the smallest value. So we know that the absolute min has to occur at one of these 4 x coordinates, and so we just have to check which one is the smallest. And we're seeing the smallest right here. The smallest value is -61. So the absolute min value is equal to -61, and it occurs at x equals -6. So we were able to figure out the max, where the absolute max occurs and where the absolute min occurs for this function. All right, let's try another example. We're going to find the absolute max and min for the function x minus 2 times sine of x on the closed interval from 0 to 2 pi. So first thing we want to do is just verify that our function is continuous. And it is. It's a continuous sum or difference of a polynomial, the x, and the trig function, 2 sine x. So we're just adding, subtracting there, a polynomial and a trig function. Polynomials are always continuous. Sine of x is always continuous. So when we add or subtract them, the result is continuous. So we know this function is continuous. We're talking on a closed interval. So this function is guaranteed to have an absolute max and an absolute min. So step 2, we want to find the critical numbers. So that means we need to figure out f prime. We want to figure out where f prime is equal to 0. Where does it not exist? So let's first calculate f prime. So derivative of x is 1. Derivative of 2 sine x is 2 cosine x. So our derivative here is 1 minus 2 cosine x. Now we want to figure out the critical numbers. So that means we need to figure out where f prime is equal to 0. And where does it not exist? And actually, let's do the not exist first. So when we're looking for how does something not exist, usually what happens is we're looking for division by 0. We don't see that here. So there's not going to be any contribution to our critical numbers from the derivative not existing. So the derivative exists on this entire interval. So we're not going to have a critical number that way. But what about where f prime is equal to 0? Let's see that. So we set our equation, our derivative equal to 0, and we're going to solve that for x. So I want to get cosine x by itself. So if I move all the terms, I get cosine x is equal to positive 1/2. And there's important values of, important angles of sine, cosine, and tangent that, it might be a good idea to have memorized. So we want to know, where does cosine x equal 1/2? And so these important angles are ones that we use in a lot of examples, and they're kind of the ones where we have a nice expression for the value of sine, cosine, and tangent. So if we wanted to figure out where does cosine equal 1/2, we go into our cosine column, find 1/2, and then we figure out the angle that gives it to us. So in this case, pi over 3. So x equals pi over 3 is one of our critical numbers. Now it turns out that if we were to kind of graph cosine x, what does the graph of cosine x look like? Well, it looks something like this. So it goes through one full cycle in between 0 and 2 pi, hits its low point at pi, crosses the x-axis at pi over 2 and 3 pi over 2. And what we just figured out is, where does it cross the line y equals 1/2? Well, we figured out the point over here, but drawing in, we see that it has to happen at a second point right over here. So how do we find that other place where cosine is equal to 1/2? Well, that second value is 2 pi minus pi over 3. So our second critical number here is 5 pi over 3. And so those are our critical numbers. So the derivative is equal to 0 at pi over 3, and then 5 pi over 3. All right, so we found our critical numbers. Now we just need to evaluate and then compare. So let's plug in. Let's do f prime, or f of pi over 3. So we're now going back to our original function, and we're going to plug in our critical numbers and our endpoints. So when we plug in pi over 3, we end up with pi over 3 minus 2 times sine of pi over 3, which is, if we want to look it up, sine of pi over 3, we find pi over 3 in our angle column, find sine, the sine column, and their value there tells us sine of pi over 3 must be square root 3 over 2. So the value of f, our original function at pi over 3, is pi over 3 minus square root 3. And just for comparison purposes, this is approximately negative 0.685. Then we do the other critical number at 5 pi over 3. And if we do that, I won't go through all the evaluation there. We'd end up with 5 pi over 3 plus square root 3, which is approximately 6.968. So those are our critical numbers. Then we want to do our endpoints. So I'm going to plug in 0, plug in 2 pi. So the endpoints of my interval So when I plug in 0, I end up with 0. And when I plug in 2 pi, I end up with 2 pi, out of kind of coincidentally there. And 2 pi is approximately 6.28. So we just got the decimals there just for comparison purposes. And what we're seeing is we want to identify then the largest and the smallest of those values. So the largest is the 6.968. So the absolute max is 5 pi over 3 plus square root 3, and that occurs at x equals 5 pi over 3. And then the absolute min is the smallest value. So we want to find the smallest value, and that is this negative here. So this is our smallest value. And we want the exact, so pi over 3 minus square root 3. And that occurs at our other critical point. So once we have our critical points and our endpoints, we just plug into the original function, figure out what the values are, and then we just compare all of them and see which one gives us the largest and which one gives us the smallest. All right, so we're going to stop there for today. We'll do a couple more examples of this on Thursday, and then get into talking about intervals of increasing, decreasing. So we'll see how to calculate those precisely. All right, so good luck on your exam for people in the Tuesday's recitation. I'll see you in your recitation for your exam. So, good luck finishing up studying. And then we'll see everyone on Thursday for Thursday's lecture.